So, in the class I discussed this Mercer theorem, and I have marked that Mercer and positive definite kernels are not necessarily included in the they are not included in the mid-semester exams, the Mercer's theorem. But the reason we discussed this was so that you get an idea that there is some underlying foundational thought process behind which kernels have been designed. Okay. So the question was, how do you come up with linear kernels, polynomial kernels and RBF kernels? Linear kernels obvious because the phi is staring at you. So polynomial kernel, I already gave you an example. In the simplest case of d equals 2, how you could actually construct the phi. But constructing the phi for every d is a painful exercise, right? And that is why we developed the Mercer's theorem. Okay, so showing existence of phi, a mapping phi from the input space to some large space, could be even infinite dimensional space, we call it in general the Hilbert space. So to show that this exists for a given k, right, kernel function, which takes 2 inputs in Rn and gives a real, right. This is the task we set out to. So what all we did we do? One, construct a phi, and that is what we did in the first case, right. Construct a phi, for example, in the case of 1 plus xi transpose xj squared, we did this explicitly. This is not always possible. The second we said is, if there is a given matrix, given a matrix of k's, right, to show that phi exists, what did you do? We did singular value decomposition, where we basically had eigenvalues greater than or equal to 0 and eigenvectors u, and you combine the two, u sigma raised to half gives you basically phi tilde transpose, right. This was what you did next. Okay, so we did this, R is u sigma raised to half, and R was basically our phi tilde transpose, and I showed you this example, a finite dimensional example. I give you this K matrix, I find that I find a singular value decomposition, I get sigma which is non-negative, all the non-negative entries here you can confirm, and then square root sigma into d, this is basically R. So the third tool, well, this is the second is really not an option. I mean, I would say it's like, it's 2A, it's really not a full-fledged option, because you have to do this for every matrix that you can generate. And the real option, the powerful generic tool to show this existence, which I call the real 2, is the Mercer's theorem. And as I said, this will be dealt with more in the post midsem. I mean, I've given you a sufficient idea, but I'll not include this in the midsem. And the idea here was to just generalize the sigma raised to half was generalized to alpha, and the u was generalized to not a g but eigenfunctions. Right. So This is the Mercer theorem. Basically the same idea. The idea in both these cases is to show positive definiteness. Positive semi-definiteness, PSD, right. In the case of 2A, the PSD nature is that B transpose KB should be greater than or equal to 0, right. This was what we had here in 2A. In 2, the option is basically in terms of integrals, x1, x2 integral, gx1, gx2, kx1, x2, dx1, dx2. You need to ensure that this is always greater than or equal to 0. So these are basically tools. I hope you got an idea, and we discussed bunch of so this I kind of gave you an idea in the class. We will do it again in the post midsem. But what I want you to consider as part of midsems is that given something, given you know something is a kernel, how do you construct more composite kernels? So for example, if K1 and K2 are positive definite kernels, then the following are also kernels: alpha 1 times K1 x1 x2 plus alpha 2 times K1 K2 x1 x2. How do you show that this is a kernel? Can you make use of 1 here? What's the tool you will use here? Could you prove using tool 1? Construct a phi. So let's say K1 had a, let's say K1 x1 x2 was say phi 1 transpose phi x1, so phi 1 basically it's in terms of phi 1, and K2 was in terms of phi 2. So could you write K, and let's call this entire thing K. Let's say this is K x1 x2. So what could you write as K? K x1 x2, let's say I want to show its phi tilde in terms of phi tilde. So what would phi tilde be? Can you recommend a phi tilde? In terms of say alpha 1, alpha 2. So alpha 1, alpha 2 are non-negative. There is a reason why they are non-negative. So that you can take their square roots, right? Does that hint help? So what could this be? So square root of alpha 1, phi 1. So basically this can be applied to any input example. So phi tilde, let's say on x, is square root of alpha 1, phi 1 applied to x. And to that you concatenate. Does this help? Is this an intuitive phi tilde? Now this is not really a rigorous proof. This is intuitive in the sense that the phi could be really infinite dimensional. But as long as inner products are concerned, you could think of having a sum of two inner products. Inner product in terms of phi 1, the same inner product on phi 1 and then on phi 2. Inner product on maybe different dimensional spaces. Is that making sense? Yeah. You basically appended the same vector, you appended. So concatenation. Does that make sense? Okay, so you can do that. So proof for the first one I gave. What about product of two kernels? K1 into K2. So let's say K1 is a valid kernel, has a valid phi 1. K2 is a valid kernel, has some phi 2. And again, we are going to be a little intuitive here because phi 1, phi 2 could be infinite dimensional. They just go to some Hilbert space H. But given they are, how do you manage K1 into K2? what would be an intuitive phi? A phi tilde. Suppose phi 1, phi 2 are finite dimensional. I mean, this is the last question I have on kernels as such, but I want you to understand how kernels can be composed. So product and linear combination are very natural. So how would you deal with product? I mean, think of this, right? Think of it differently. So one way is, okay, you can say that this is as follows. I am going to write the expansion here, which is phi 1 transpose x1 phi 2, sorry, phi 1 x2, and from the second component I am going to get phi 2 transpose x1 dot product with phi 2 x2. Now does this give you some idea? Could I take some combination? Can I get all the x1 components together, the x2 components together? What would the product really look like? Can you use the fact that sum of products, since let's assume we're dealing with finite dimensions, okay? Assuming there are finite dimensional phis, can I write sum of products? This is basically a product of sums. Can I write a product of sums as sum of products? So each of them, for example, this is a sum over j of phi 2 j x1 phi 2 j x2, and this is a sum over j phi 1 j x1 phi 1 j x2. So can I write this as a product of sums? As a sum of products. This is sum of products. So, whereas what you have here is as a product of sums. You are multiplying this sum with this sum. How do you write this? Now this should be obvious, right? For all j, all k, phi 1 j, phi 2 j, phi 2 k. That makes sense? Or let me not use index j at all, little confused. So let's say sum over I, sum over k, phi 1 I, x1, phi 2 k x1 into phi 1 I x2 phi 2 k x2. Is this correct? Okay, so I just again remind you, for simplicity, we assume that the phi is finite. So phi, by phi we mean phi 1 for k1 and phi 2 for k2. Both are finite dimensional. So can you now suggest a phi tilde? Anyone? A phi tilde that will give me the kernel for the phi for the product. Yes? What comes to your mind? So can I just couple these two and say that phi tilde x is going to be a vector consisting of all phi 1 I x phi 2 k x for all values of I and k, long vector. So basically I'll take all possible product. So this is also called an outer product. I mean, this results from an outer product. All possible combinations. Is that making sense? So basically some positive linear combination and product of kernels are both kernels. Okay, so you can now think of whether exp of inner product is also a kernel. It's called the exponential kernel. So I am not expecting a very rigorous answer, but think about it. I mean, could you express exp also in terms of a polynomial? You can, right? Does that help you? Okay, so think about it. And also the RBF kernel, could you do the same thing there? We are not again, we will revisit the Mercer's theorem after midsems. So there are also other kernels. So kyx, that RBF kernel, another view of kyx is also as a smoothing kernel. I mean, we will see that, hopefully we see that soon. Okay. So in tutorial 4+5, there are problems informally show that kernelized logistic regression form is equivalent to the original logistic regression. So in the tutorial 4+5 and also is in the lab, we talk about this kernelized logistic regression. And another problem is show that ridge regression has an equivalent kernelized form. So I am basically solving the tutorial and also helping you with the lab. Okay, as that part of lab 3 and tutorial 4+5, and also be part of midsems. Okay, so let us recap logistic regression and then try and see what the kernelized version will mean. So all of you remember this objective, right? Cross entropy, we have given interpretation to cross entropy plus a regularization term. This is called cross entropy, where you are trying to encode the data that you see using a model distribution. The data is yi, the model parameters are sigma, the model is coming from the sigma, and you have the regular, this cross entropy loss including the negative sign, and this is the penalty, regularization penalty. Okay. Now can we view this in a dualized, in a kernelized form? What did we do for perceptron? We just rewrote the decision function and also the update rule, right? That is why when we got to the kernel trick. So what we will do here is do a little bit of manipulation on the cross entropy itself, and it's very simple. All we are doing basically is substituting for sigma. So sigma was our model distribution, the logistic function. So when you substitute for sigma here and expand, you are able to simplify it, write it differently rather, in this form. It is a summation over all examples yi times w transpose phi xi. What does this remind you of? Perceptron. I mean, so now there is a reason why we get it to this form, because then I'm kind of hopeful similar trick would work. So this is this perceptron loss, somewhat like a perceptron loss. There is some additional term and there is a regularizer. Okay, then one more step we will have. Okay, so now we will from this we will kind of make a jump, a kind of leap of faith, and the fact that there is a dual kernelized objective comes from something called the representer theorem, which again we will do post midsem. But what would you do? I mean, if at this form this looks close enough to the perceptron loss, what is the form of the decision function in terms of the kernel? What would you think of? Yes, so the suggestion is a similar form as what we had for perceptron, summation over all examples of alpha j times k of x comma j. The only difference will be that in perceptron, because we had a hard thresholding, we could write the decision function directly. Here we are dealing with soft thresholding, we are dealing with a sigmoid function. So the effect will be again sigmoid. It will basically be in an exponentiated form. Okay. So it's basically exponentiated form of the weighted sum of kernels, and that's the intuition, right? The exponentiated form of the weighted sum. So the first part is exponentiated form is because of sigma soft instead of hinge loss. You might remember what perceptron was handling was the hinge loss, the hard hinge loss, which is hard. Okay, and this is how it will be. So sigma w, I'll write this a little bigger here. So what you have is in the denominator, this term is enlarge this. The same thing which you expect, summation over j of alpha j k of x comma xj. This is exactly what you expected, but now that's sitting exponentiated in the denominator exactly in the form of sigmoid. I mean, this basically has taken the place of W transpose phi x. Okay, so the basic idea is wherever you have a dot product between the parameter vector and the feature, that's exactly where you have now a weighted sum of kernel evaluations over all the examples with respect to your query example. Is this clear? So this sigma is basically what will change throughout. It will change both in the objective as well as in the decision function. The objective will also change here. So the same substitution. Again I point out. So let's just contrast quickly here. So you have all these terms, wherever you have k, you'll have this summation over j, this part, and likewise ki alpha j. So all these are now in place of W transpose phi xi. Wherever you have W transpose phi xi, you have this term. Okay, and then W square is actually, you can think of W square also now. W is also kind of accumulated over all the examples, right? I mean, I give you in the perceptron, I explained how W keep getting accumulated as the iterations proceed, and that form of W is basically what leads to this component. The regularization basically results in alpha j products, I mean products across xi's and xj's, multiplied along with the kernel evaluation on xi and xj. Okay, so this is the kernelized kernel logistic regression model. Okay. Again, I am not looking at any rigorous proof here. It's just kind of intuitive correspondences, also inspired by our experience with perceptron. Okay. Now this kernel itself could be compositions, right? It could the kernel itself could result from alpha 1 k1 plus alpha 2 k2, or it could be k1 into k2. The kernels now that sit here could be simple, elementary or complex kernels. So I will also build a background for kernel linear regression. So we will illustrate the kernel trick on linear, basically ridge regression. So just recall the ridge regression, basically it's penalized or regularized least square regression, where you have phi w minus y norm square plus sigma or whatever, some regularization component with respect to norm w square. And this is what we got basically because of map estimation. And yeah, and we said that we will just use a single lambda instead of this lambda sigma square. This just replaces with a lambda. Okay, and with that we got closed form solutions phi transpose phi inverse phi transpose phi for linear regression and ridge regression, phi transpose phi plus lambda I inverse phi transpose y. Now I want to ask a simple question. Phi transpose phi, would it involve kernel? Would it involve kernel computation? Try write down phi. What is the form of phi? Phi is, every row of phi is, what is every row of phi? One example, right? Phi x1, phi x2, blah blah blah. Now if I take the dot product of this, if I take the transpose of this and multiply it with phi, what will happen? Does it directly give you the kernelized form? How many of you feel it will immediately give you? Is phi transpose phi the form we actually are interested in? What is the form we are interested in? Phi into phi transpose. How did you guess that? R. Okay, so you got a hint from our discussion earlier where we did the SVD decomposition. There we got R, and R was basically the transpose of phi. So that's the only dikkat, that it is not readily in the form we want, and I'll just quickly run you through this. So we talked about polynomial regression, a degree 3 polynomial. Each bend to the curve corresponds to some increase in norm W, right? In fact, in tutorial 4 plus 5, there's a question on how eigenvalues of phi transpose phi plus lambda I indicate of the curvature, how curved this resulting regression solution would be. Now the question what we are trying to do? We are trying to say, well, why do you need a polynomial phi? I will use a polynomial kernel, right? So the our goal, achieve polynomial fit by employing a polynomial kernel. Right, in general our polynomial kernel is x comma y, kx comma y is 1 plus x transpose y raised to d. Same effect we want. Okay, so the first thing is we are going to note a difference between matrix phi and the vector phi x. So matrix phi, as we already noted, every row is basically the phi applied to that example. Okay, this is phi applied to x1 and phi applied to x2. And now we are going to quickly look at what the regression function is in terms of a substitution. So let's write down the regression function. This is what I would encourage you to do. If I want to see whether there is a kernelized form, I look at the decision function. Fx is w transpose phi x. Substitute the value of w. That's what we have done here. We have substituted the value of w, which is the entire expression, phi transpose phi inverse phi transpose y. Right? This is the value of w that we have substituted. And as some of you pointed out, this is not really in the kernelized form. So recall that phi transpose phi xi transpose phi xj is kxi xj. So now we are going to very, very specifically note down differences between phi transpose phi and phi transpose. Okay. So you tell me please what this capital phi transpose phi, its ijth entry will be, what the ijth entry of phi transpose will be. It would be nice if everyone writes it. So this is central to our understanding of kernel linear regression. So anyone? In terms of simple, you'll need to introduce some additional indices, yes? Good point. Phi transpose phi will be the covariance across features. It's not the relationship across examples. So covariance across features I and j, right? Whereas this we expect it to be basically k of xi comma xj is similarity between examples xi and xj. So specifically if you write down the expression, this is what it turns out to be. This is summation over all indices k, examples k for ith and jth feature. This is the covariance. I mean, I'm using covariance in a loose sense here. So it's rather, you can say that it's an indication of covariance. Indicates covariance. The second one is indeed the summation. So here in the second case, we have a summation over the index k, which is k ranging over features, where xi and xj are fixed. Okay, so you see the difference here. Okay, so now the question is, if you are kind of okay with this so far, how do I go from phi transpose phi, which is a covariance indicator, to a kernel indicator, which is of the form phi phi transpose? So the question is how to transform. Okay, so we will make use of a matrix identity, and the matrix identity I will show you, and you can just verify that the matrix identity actually holds for scalars. And we will take a leap of faith that you can apply the same matrix identity here. Okay, so to consider this matrix identity, okay, so P inverse B transpose R inverse B, the whole inverse B transpose R inverse. Now what happens here is, in some sense you are able to, so if you think in terms of reciprocals, let us just think in terms of reciprocals. So think that this is 1 upon P, so 1 upon P plus B into 1 upon R into B, 1 upon the whole thing times B times 1 upon R. Okay, this is in terms of scalars. What are we saying here? Well, if it were scalars, I could actually take the R inside, isn't it? This is 1 upon this whole thing. So if it were scalars, so this is what I am multiplying. I could take the R, 1 upon R, and absorb that R here. I could just multiply the whole thing here by P. Is that correct? And basically get rid of this 1 upon P, bring a P here. So that's exactly what's happening here. You can see that basically it's P and R that have kind of changed roles. Of course, you have to also deal with the fact that you are dealing with matrices, they are transposes. But intuitively that's what is happening here. So you can verify that this is nothing but P into B divided by B plus R. So in this process, I have basically taken this R in, so R inside here to get rid of the 1 upon R, and I have multiplied this whole thing by P. Okay. So now if you think this identity is correct, now just last step here, substitute R equals I, P equals 1 upon lambda I, and B equals the big matrix phi, and see what happens. Okay, so what happens if you say R equals I, P equals 1 upon lambda I and B equals phi? Write down the expression. So P inverse will become, what will be P inverse? Lambda I plus B will be phi, so phi transpose, R will be I and again B phi, so this is what you will get, inverse B which is again phi, R inverse which is I. Okay, so phi transpose phi plus lambda I inverse phi. This can be rewritten as 1 upon lambda I times B transpose which is phi transpose, BP transpose which is basically phi transpose plus R which is I, the whole inverse. Okay, this is basically the identity. This entire expression here is what I am going to substitute with the right hand side. BP transpose. There is a lambda. Yeah, you are right. 1 upon lambda. 1 upon lambda. Okay, so now if I just substitute, I should be done basically. I just need to substitute it here. Now, is this the desired form? Earlier we had phi transpose phi, which was like indicative of covariance. Now what do we have? Phi transpose, exactly the form that reflects the computation of kernel similarities. But there is this phi transpose hanging outside here. Uska kya kare? What happens to this phi transpose? When you substitute here, this this entire expression, what happens? What is sitting here? Phi transpose x. That still is going to operate, right? You still have this phi transpose x. So let's write down the final expression. Get phi transpose x times this 1 upon lambda I can be just 1 upon lambda sitting outside here. Phi transpose. This 1 upon lambda can actually be all taken care of easily by pushing it inside. So I'm just going to simplify my life. Phi transpose. This is what you get, right? If I substitute, this is what you will get overall. Okay, but just remember that this phi is basically, this phi transpose is basically this vector, and this is a row vector. Whereas in phi transpose you have columns as the phis. So, this is how textbooks use it. I think I'll just recap. Need know the difference between matrix phi and vector phi x. There's a slight difference. Vector phi x is a column vector, matrix has the phi as its rows. Okay, so with this basically you will find that you're just substituting all this. You find that the decision function is actually completely kernelized. It's completely in the kernel form. Here, fx is summation over I alpha I phi transpose x into phi xi. W is also of the same form, phi I xi, and then this alpha I is basically this component. You actually don't need W at all. You don't need W because anyways you're looking at closed form solution. So I'll erase this part. Yeah, this is what you focus on. Fx is basically completely kernelized. The closed form solution where alpha I is also in terms of kernel entries. alpha I is phi transpose. Okay, I hope this helps you solve your lab 3. So this is the summary of ridge regression. The decision function is completely determined only through phi transpose phi, and now by now we already are familiar this can be written as k of xi comma xj. All these are basically kernel entries. That's it for what I needed to cover.